Hello, good afternoon. Can you hear me? We're going to start very shortly. Only 8 people joined in. Not that many. Nevertheless, we'll start. Everyone, could you please just signal, can you hear me? I can't see your responses. Yes, number 1. Already good. Yes, okay, fine. We're about to start. So, okay. So let's recall what we have been doing. We were investigating a joint model of stochastic dynamics of 2 assets in the hope that we can get something useful from that model. So once again, you remember we had 2 stochastic processes, xt, which was the price of, for example, BTC USD, for example, right? YT, which was, for example, price of, I don't know, Ethereum USD. Or, I don't remember which examples I was using. Oh, sorry. It was probably USD RUB. Or Euro RUB. Yes. Then what we did, we constructed a system of 2 stochastic differential equations trying to capture some kind of joint stochastic dynamics of these 2 assets. So it was in the form you remember DXT was excuse me, please, can you, I'm really asking you to remind me, is it what we have been doing in the last lecture? Because I have a very similar bachelor's level course. And I could have very easily confused what I was talking about in that course and in our lecture here. Can you please remind me? So we're studying 2 stochastic processes with a joint dynamics, is it correct? I'm not mixing up anything.
Excuse me, last lecture was...
Who remembers what we have been doing last time?
It was about solving
I'm continuing from that point on, but if you didn't see it last time, then you would be in trouble.
Sorry, can you
Nobody
hear me?
asks what we have been doing? Okay, let's continue then. So, we're considering a model in which there is an interdependency in trends. So for dxt, we will put some coefficient a1 xt plus b1 yt plus c1 dt plus some structure of the volatility. So there would be, let's say, some function sigma 1, 1 of whatever. In general, sigma ij are functions of xt, yt, and t, and possibly some parameters. Okay. dwt plus sigma 1, 2 dzt, where we assume that dwt and dzt yes, you're absolutely right. So today we're going to talk about biased and unbiased estimators, precisely. So the estimator which we are going to obtain from this model is in general going to be biased, and then we'll decide how to make it unbiased. Absolutely. So Marie, you're right. Yes, thank you. That's exactly what I was going to talk about. So they're independent, and therefore this means that the product of dwt dzt would be equal to 0 in terms of the expected value. And the high order terms are dropped in this model. Similarly, we have dyt equals to a2 xt plus b2 yt plus c2 dt plus sigma 21 dwt plus sigma 22 dzt. The first thing we did, and you remember that, we realized that the stochastic terms up to a coefficient are the Brownian motions. So this stochastic linear combination sigma 1 1 dwt plus sigma 1 2 dzt can be written as, I think we did it, a1 dut, where dut is another Brownian motion. A1 would be equal to square root of sigma 1 1 squared plus sigma 1 2 squared. Okay. Similarly, the second one would be equal to a2 dvt. A2 equals to square root of sigma 2 1 squared plus sigma 2 2 squared. Where, if you remember, dut dzt dvt are again Brownian motions, but now correlated. If we denote the correlation coefficient by rho, So it is a correlation coefficient between dut dvt. Then we have shown that this correlation coefficient was equal to, you remember what was the expression? It was sigma 1 sigma 2 plus sigma 1 sigma 2 the cross product over the square root of sigma 1 squared plus sigma 1 squared times square root of sigma 1 squared, yes, sigma 2 squared plus sigma 2 squared. And then we can say that with this correlation coefficient, it is correctly to say that's important, that the product dut dvt, now correlated, would be equal to rho times dt. Okay. Then, sorry, we don't remember. No, Maria already remembered, therefore we're on the right way. Okay. What do I want to do next? We would consider, you remember, some time series of observed values for our process. So let's say we have time series. We have t0, which I can say is 0, and so on, some ti minus 1, ti, and so on, some tn equals to t capital. And we have vectors of observed values, xi, yi, and so on, at this time instance. In order to calibrate our model, what does it mean, calibrate our model? We don't know the parameters of the model. Params are unknown. So we don't have, first of all, the matrix A, which is A1, B1, A2, B2. We don't have it. We don't know the vector C, which is C1, C2. Even if we assume these are constants, we don't know them. Regarding sigmas, we need to model them. So the structure of our volatility terms can be any. So for example, in the volatility model, many situations are possible. Typically, what are standard volatility models we can use? Volatility means sigma. Sigma models. Here, multiple situations are possible. If you remember, just some examples. It could be CV, constant elasticity of variance, in which case sigma 1 is, for example, x is some constant, which I will denote by, I don't know, sigma 1 bar, x, sorry, not s, but x, x xt to some power beta 1. Sigma 1, 2 would be a constant, sigma 1, 2 times yt to the power, let's say, this is 1, 1, this is 1, 2. Sigma 2, 1 is sigma bar 2, 1, xt to the power beta 2, 1, sigma 2, 2 is obviously another constant, sigma 2, 2, yt to the power beta 2, 2. Already here in A and C, we have 6 unknown parameters, right? Okay. In here, we have plus extra, actually for each entry of our correlation structure, we have 2 parameters, sigma bar and beta. Therefore, we have plus 8 wall params. That's for CV. We may have another model, which is the Lipton I think it is Lipton volatility model. Let's say each sigma ij is in general a polynomial up to quadratic terms in both xt and yt. So we would have, in general, it could be a constant even, so it would be sigma ij 0 plus sigma ij 1 xt. These are not powers, these are indices. Let's use bars. Sigma bar ij 2 yt plus sigma bar 3 ij xt squared plus, we may or may not use factor 2, let's say not, sigma ij 4 xt yt plus sigma bar ij5 yt squared. So for each sigma, we have therefore 6 parameters. Therefore, we have plus 4 times 6, 24 wall params. Which is quite a lot, actually. We may have an affine model. Affine model is a very important, in general, class of models. Okay, what that? That's from another presentation. Oh my god. I will need to scroll it. Sorry. Oh, that's our previous one. Scroll, scroll, scroll. Scroll. Okay, at last. So we may have an affine model. In which case we are not considering the structure of sigmas themselves, but you remember we had the covariance matrix C, which was our matrix sigma times sigma transformed, which was precisely, if our sigma was sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2, multiplied by itself transformed, sigma 1 1, sigma 2 1, sigma 1 2, sigma 2 2, which was, let me denote it by C 1 1, don't confuse it with the vector C. C1 1, C1 2, C2 1, C2 2, where C1 1 is actually, as you can easily see, sigma 1 1 squared plus sigma 1 2 squared, and this is actually our A1 squared. You remember A1 coefficient. C1 2 equals to C2 1 equals to sigma 1 1 sigma 2 1 plus sigma 1 2 sigma 2 2, which is the covariance term effectively, and C2 2 is obviously sigma 2 1 squared plus sigma 2 2 squared, which is our coefficient A2 squared by our definitions. Then under the affine model, we assume that those C coefficients are linear functions of our state variables. So let's say Cij equals to alpha ij xt plus beta ij yt plus gamma ij. This means there are three extra, well, not exactly. How many independent coefficients do we have in this case? We have obviously C11, C22, and these two are equal, C12 and C21. Therefore, we have only three coefficients which are representable this way, and this means that we have, in addition, 3 times 3, therefore 9 wall params. So we have volatility params and the original parameters which are given by the linear terms in the matrix A and in the column vector C. So basically all params can be put into a vector Q, and this vector Q is actually matrix A, if you remember, vector C, and wall params, as many as we have. So there are 6 here and a variable number here, which depends on the model. In general, it is undesirable to construct models with too many parameters, because these parameters are difficult to estimate, or as we say, difficult to calibrate. And for that reason, we can very easily get an overfitted model which would perform reasonably well in sample when we calibrate it on historical data, but it would have very poor predictive power in that case. Okay, so our problem is to estimate Q as we discussed probably already, estimate Q
Профессор, could you hear me?
based on time series
Professor, could you hear me?
when for a given Ti we have the value xi and the value yi for I from 0 to n. So that's the problem of estimation. Now we will do what we're already, I think, quite familiar with. We will use the maximum likelihood estimation. It is not the only one possible, but let us use it. So we'll use maximum likelihood. We construct the likelihood function L, which depends on our parameters Q, which, once again, you remember we were doing this maximum likelihood for one-dimensional case, but now we are doing it in two-dimensional case. In one of our previous lectures, we were considering maximum likelihood estimations in 1D. Now it is in 2D. Therefore, again, our likelihood function, our log likelihood immediately, it is a sum from I1 to n log of the probability density, log of the probability density of our process in the point xi, yi at time ti, conditional on being in the previous point xi minus 1, yi minus 1 at time ti minus 1, and under the vector of our parameters q. Again, we are conditioned here only on the previous point due to the Markovian property. It is a Markov model of our process, of the process given by the two-dimensional SD. Okay. But the question is, we need this density. So how can we compute this density, this probability density function? This is a PDF. Now it is a joint PDF. P is a joint, not one-dimensional, but joint probability density function of the process xt, yt, conditional on what we have put here. There are several ways of how this joint probability density function can be computed. what in general have we been doing in order to compute the probability density function for a one-dimensional process? Remember when there was a one-dimensional process given by a stochastic differential equation with DST? Which machinery have we been using to that end in order to compute the density?
Oh, sorry, can you hear me?
Your replies, please. We did something very, very, very important. Yes. One new message. Can you please repeat?
Sorry, can you hear me?
Yes, I do, yes.
I have a question. Is this a lecture that is connected to the previous one we have?
It is connected, yes, definitely. We are going to show several methods of how we construct this density.
Because the correlation is new for me. That was on the previous slide.
I did not denote it by a row previously, but we did derive this correlation. I'm absolutely sure. We computed the covariance and then the correlation.
No, we didn't. Sorry.
We didn't?
We didn't.
Okay. But yes, so our previous topic was about locally normal approximation, and indeed that's how we do it. If you would like it to repeat, that's very easy actually. Okay, thank you for asking this. So basically,
sorry, our previous lecture was about log likelihood. I guess we were deriving log likelihood from our to solve our stochastic differential equation.
Okay, so not to solve, but to compute the densities. Okay, that's okay. So what we sorry, I see your point. Yes. So now we're in a two-dimensional case. So to put a little bit in context, thank you for pointing it out. So you see what we did previously. Recall. Okay, sorry. Previously we had a one-dimensional case. One-dimensional case. With the equation in the form dst being some kind of function mu of st and t dt plus some function sigma. Okay, let's do a brief recap. Sigma of stt dwt. Then there are two ways of how we could construct, again, we're interested in the probability density function of this process at some point si, conditional, si at time ti, conditional on the previous value si minus 1 at time ti minus 1, and possibly some model parameters q, where model parameters q are here in mu and in sigma. So our problem was this. So what I would like to recall is that there are two ways of how this probability density could be obtained. One way is by solving the Fokker-Planck PDE. That's what I actually wanted to hear from you. We definitely discussed this. So the method one is by solving the Fokker-Planck PDE. There would be a partial differential equation, dp dt equals to minus partial derivative with respect to s of, so we want to obtain p of s and t under all those conditions, p multiplied by our function mu plus 1/2 of the second derivative with respect to s of p multiplied by sigma squared under the initial condition p of s at time 0 being equal to the delta function, direct delta function of s minus s0. And under suitable decay condition at the infinity, so we would say p of plus minus infinity at any t. So this is the initial condition. And that would be 0. So our probability density function is decaying at the infinity. This is a boundary condition. That's method number 1. It works in general, but as you remember, in very, very few cases, we were able to obtain an analytical solution to this Fourier-Planck partial differential equation. In most cases, it would require a numerical solution. All right? In most cases, requires a numerical method. And we briefly discussed how this numerical method could be implemented. It is rather unpleasant that our numerical scheme starts with a delta function to begin with, but due to the presence of the diffusive term here, this delta function quickly decays, if you remember our discussion, and we get typically a valid numerical method for constructing our probability density function. So that's okay. Method 2, a much more simple one, use locally normal approximation. So basically we would say Si from this equation, we would say Si equals to Si minus 1, approximately of course, plus mu of Si minus 1 Ti minus 1 multiplied by the time step 2i, which is Ti minus 1 plus sigma again, and also depending on our parameters, sigma evaluated in the previous point Si minus 1 Ti minus 1 and q multiplied by some normally distributed random variable z, which has a normal distribution with 0 mean and the standard deviation being the square root of 2i. In this case, we could see that why it is easy in this case, because Si would be normally distributed. Oh. Okay, in which case SI itself my screen movement is very slow. Oh, okay. SI itself would be normally distributed with this mean SI minus 1 plus mu mu of SI minus 1 TI minus 1 times tau I, and the standard deviation being equal to sigma of SI minus 1 TI minus 1, implicitly assuming that it depends on Q as well, times square root of tau I. And from this locally normal distribution, we of course get a locally normal PDF. Locally normal PDF for PDFP. If you remember, we would have P of SI TI conditional on the previous point would be equal, of course, to 1 divided by the square root of 2 pi under the square, sigma 2 pi, let's say, under the square root, we'll put it that way, under the square root tau I multiplied by sigma evaluated in point I minus 1, I mean this, times exponent of minus 1 divided by 2 times tau I sigma squared at point I minus 1, Si minus Si minus 1 minus mu I minus 1 tau I squared. Again, it is a local approximation, of course. Or we had method number 3. You remember we discussed that although this approximation is valid, but it is generally quite rough. And for that reason, we would apply the F transform first. So we would have xt being equal to F of st and t. And you remember that it was actually an integral from some initial value s star to st du divided by sigma of ut, and then our equation would be rewritten, and we would have, after we get into the xt space instead of st space, we would have a more accurate approximation. You remember we discussed that, and another log likelihood problem in the xt space. So we would have dxt equals to new trend mu tilde of xt t dt plus 1 times dwt, and then we apply again the maximum likelihood estimation in the xt space. But you remember But beware, you remember we discussed a pitfall, why it was not okay to construct the likelihood function directly in the xt space, and we had to return effectively to the original st space for the observed function st, and the result would be different. It would be actually different by precisely this division over sigma t. So basically the new likelihood function to be maximized would be given by if you remember, it was L x of q would be sum from I1 to n log of the probability log of the probability density function in the x space of xi ti conditional on xi minus 1 ti minus 1 and parameters q divided by, you remember, it was precisely this multiplicating factor sigma of si ti and q. Without this sigma we would have an erroneous result, and that would be again maximized over q. So that's what we have been doing in a one-dimensional space. And in one-dimensional space, okay, jumped a little bit too quick to two-dimensional one. In the one-dimensional space, whatever maximization method we use, we eventually obtain some estimation. Let me denote it by q hat, estimated vector of params. Estimated typically by doing what? By maximizing the likelihood function. By maximizing. How this likelihood function is constructed? Well, there are at least three ways of how it can be done. And obviously, depending on the way of how we construct it, we would always get slightly different results. These are only estimations. And also, it is very important to understand that if we view our inputs, for example, xi and or si, as manifestations of a random variable, then this estimation function maps the original random input into a random result. We run an estimator on the random input, we obtain in general a random estimated vector of params. So q can be considered, can be viewed as a random variable. So the question is whether we can say that the expected value of our estimated set of parameters q indeed equals to, let's say, q0, which is true params. Obviously, being random variables, they can deviate from the expected value. Our question is whether, deviate from the true values, but the question is whether at least the expected value of our estimated parameters equals to the true parameters. The answer is, and if yes, we call it unbiased estimator. If no, we call it biased estimator. So in general, unfortunately, there is absolutely no reason to believe that MLE estimators are by some magic unbiased. Unfortunately, MLE, E stands for estimator itself, so saying MLE estimator is probably wrong. MLE is a biased method. Even when the transition densities are known exactly, like for the Ornstein-Uhlenbeck problem, we can still get biased results, even if P of, let's say, Si Ti conditional on Si minus 1, Ti minus 1, and Q is known exactly. Only in a very, very limited number of cases, when, for example, the process under estimation is a normal one or a log normal, then we can hope that the estimator can be unbiased, and in some rare cases we can prove that it is unbiased. In general, it is biased. So in general, we would have expected value of hat is equal to the true values plus some bias, which depends on the true value. The question of whether this bias tends to zero as, for example, the number of points tends to infinity, which we consider. The answer is, again, not always. So we really have to deal somehow with these biased estimators. First in the one-dimensional case, and then we'll be returning to the two-dimensional case, to which I jumped a little bit earlier, not finishing this. Okay, how can we deal with the bias? Several ways. Obviously, if we know the bias as a function of Q0, then we can, if, for example, this bias function is known, then we can remove it from the estimation, and we will get an unbiased estimation. So if obviously if we will need to construct, just a second, I will take the call and get back to you, sorry. Hello, да, у меня лекция идет. We would construct a different estimator. We would do, we don't know Q0, so we only have an estimator Q. So if bias as a function of Q0 is known, how do we construct an unbiased estimator? We do a new estimator, which is our Q hat minus minus some character. Character, we don't know the true value, so the character depends on Q hat as well, such that the expected value of Q hat minus the expected value of the character of Q hat would be equal to 0 now. We don't know the expected value of the character of Q hat. We only know this bias function as a difference between what we do know. We do know expected value of Q hat minus, not the expected value of character, but minus the bias function, in which case minus the bias function minus Q0. So minus Q0 minus the bias function of Q0. And that we know, if the bias function is known, then we really know that it must be 0. But how to compute the expected, construct the character function so that this equation will be satisfied? It really depends. So there are several ways of how this character can be constructed. So in a very simple case, suppose that the bias function is linear. So in this case, if the character is linear, then we can, if the character is, in that case, is linear as well, in our Q hat, then assuming that it is linear, so for example, suppose that character of Q linear is, let's say, A times Q plus B, something like this, then what can we say? We have expected value of Q hat minus the expected value of the character, but that will be minus A, again, expected value of Q and minus B equal to 0. Therefore, expected value of Q hat would be equal to times 1 minus A would be equal to B. And in this case, expected value of Q hat would be equal to B divided by 1 minus A. On the other hand, 1 second, please. I will need to connect another power source to my computer because it is going to die soon. 1 minute. we're back. We're back online. So what would be? Let's see. What would be the easiest way of dealing with this? Um, so once again, sorry, we got this, and suppose that our bias is a linear function. It is the same as assuming that the character is a linear function. Maybe it's easier this way. So if, let's say, bias of Q0 is a linear function, let me, in order not to confuse it with those coefficients, I would say it is A0 times Q0 plus B0. So it would be typically this A0 and B0 are probably small, but it depends. Therefore, we would have the expected value, and then the true value, then the expected value of Q is going to be Q0 plus this bias, which is a function of Q0, which is 1 plus A0, our vector Q0, plus B0. But in fact, what we have obtained this Q. Therefore, in order to obtain a bias-free estimation from this, we would obviously solve this, obtaining the true value as Q0, being Q. This is in the vector case. This B0 needs to be a vector as well. This would be therefore Q hat minus B0 divided by 1 plus A0, and assuming that A0 is small, hopefully, we would have this is Q minus B0 times 1 minus A0 and so on. And therefore, it would be Q. Yes?
It is very confusing for me. What is Q with hat and Q with arrow?
Once again, just a second. Shouldn't be confusing. Stop here. As a result of our estimations, we somehow obtained the value Q hat. So let's do once again.
And Q with arrow is the real.
Q0 with arrow is the real one, yes.
Okay, thank you.
And once we got Q hat, then by applying this simple correction, we can obtain the true value. That's what I wanted to do. So Q0 by itself, again, we can't be sure that it is the exact value, but we now know that the expected value operator applied to the right-hand side is indeed equal to Q0. So if we just a second, then want to stop. Sorry, my screen is very, very, very slow.
Can you please repeat what is the Q0 here?
Q0 arrow is a true value of our parameters. Q
Okay,
hat
so
is the
what does
estimated value.
the bias of Q0 mean?
The bias of Q0 in this case is precisely the difference between the expected value of Q hat and the actual Q0.
Ah, okay. I think it's better to note it as bias Q hat, maybe.
One second, I'm just waiting for my screen to be writable again. So once again, Q hat is a random variable, a random vector actually, a random vector which is a result of estimation. A result of estimation, okay? Q0 true values of params, okay? Suppose that we want expected value of Q hat, we want it to be equal to Q0, but it is not. So minus Q0, we would say ideally it is 0, but in reality, suppose that it is some function of Q0. We can't say it is a function of Q hat, because Q hat is a random variable. It is some function of Q0, because Q0 is deterministic. Then we would like to apply a bias correction procedure. So basically, this function is precisely called bias. This difference is precisely called bias, which is a function of Q0. Suppose that we found this bias somehow analytically. It's not always the case. Suppose that it is analytically known. How can we correct our estimation in order to remove the bias? So in general, instead of Q hat, correction, instead of Q hat, we'll need to consider another function. Let's say, what are the values? Q bar. Instead, consider Q bar, which is some function, let's say phi of Q hat. And we now really want this function phi of Q hat, the expected value, being equal to Q0 itself. But the question is, how would we find this function, phi of Q hat? How can we find the function which, after being applied to our estimator, would give us the exact value of Q0? The simplest way of how we can do it in general as well, but the simplest way of how we can do it is to consider the case of a linear bias. in case when the bias is a linear function, and in the small it can always be considered a linear function, then it is relatively easy to do. So how to find phi? Suppose the bias is linear. So in this case, we are back to the original discussion. So bias of Q0 equals to sum A0 Q0 plus B0. That's our assumption. Because typically the bias is small, we can always linearize it and really represent it as a linear function in general. So if it has any high order terms, expanding it into Taylor series, we would drop high order terms in this case. So in that case, if the bias is a linear function, we do the following.
Can I ask a question?
Yes?
Can you please speak about the importance of that the estimator is unbiased? Like, I don't know why applying maximum likelihood estimation only without correcting the bias is not enough.
Indeed, applying, you are absolutely right, applying the maximum likelihood method without correcting for the bias is only halfway of solving the problem. In particular, I can give you one particular example regarding this. Is that, maybe you have seen it, yes. If, for example, we have an Ornstein-Uhlenbeck problem, Ornstein-Uhlenbeck. DST would be equal to kappa times theta minus st dt plus sigma dwt. In this case, we don't even need to approximate the density. The probability density function of Si conditional on Si minus 1 is known analytically. It is a normal distribution, not a standard normal, but it is a normal PDF. But when we, and the vector Q, which we need to estimate in this case, is obviously a vector of 3 parameters, kappa, theta, and sigma. What happens in practice when you apply the maximum likelihood estimation to this problem is that sigma is unbiased. Let's say our vector Q estimated is the estimated value of sigma, theta, sorry, I do it in the wrong way. So kappa, theta, and sigma. So what we have in this case, sigma is unbiased, and moreover, it is a random variable, and the standard deviation of sigma minus the true value sigma, it really tends to 0 as n tends to plus infinity relatively quickly. So estimation of sigma is the easiest one to obtain. Okay. For theta, the situation is the following. Theta is also unbiased. One second. theta is also unbiased. But the standard deviation of our estimated theta minus true theta I don't really remember what it happens. Either it doesn't tend to zero at all, here it does tend to zero quick, or it tends to zero only very, very, very slowly. As far as I remember, I will double check this, ask me next time. I think it doesn't tend to zero, as n tends to plus infinity. So the mean is correct, but the standard deviation doesn't decay, which is a rather unfortunate situation. And kappa is biased, and it is biased to such an extent that the sign of kappa may become wrong. And this is a very unpleasant situation, because obviously the larger our kappa is, the more pronounced the effect of mean reversion in the Einstein-Uhlenbeck model is. When kappa tends to zero, then there is no mean reversion anymore, and we have just a Brownian motion with the volatility factor sigma. And if kappa tends positive, then instead of mean reversion, we have an explosion. So the process oscillates to infinity rather than converging to theta probabilistically in the long run. So getting a wrong sign of kappa is a very, very, very significant problem in this case. And in general, the method, this method, it significantly, the maximum likelihood underestimates kappa. So we typically have in those situations that the estimated kappa is less than kappa zero. So we may have that, let's say, kappa zero is positive and everything is okay, but the estimated value of kappa hat is less than zero. So that's possible. So without examining our method for the bias and correcting the bias, we wouldn't be able to solve our problem. So that's the problem, right? So once again, if the bias is a linear function, linear bias, continued, then we have expected value of our Q star equals to the true value Q0 plus bias, so plus A times Q0 plus B. This is linear bias. And now it is relatively easy to see what we need to do in order to correct it. So it is 1 plus A times Q0 plus B, where B is a vector, sorry, B0, where B0 is a vector. Scrolling once again. So now we probably understand what we should do. Wait, That's what we should do. Oh my god. My Paint desktop is not responding. Let's wait. Oh no, we're back online. We're alive. Now, instead of Q hat, consider Q bar such that Q hat equals to 1 plus A. We're using this relationship 1 plus A Q bar plus B. Or Q bar equals to Q hat minus B divided by 1 plus A. Then it is elementary to see that the expected value of, Q bar, that the expected value of Q bar, and you estimate, is 1 divided by 1 plus A by linearity, the expected value of Q hat, minus B divided by 1 plus A, but the expected value of Q hat is given by this, so it is 1 divided by 1 plus A, the true value Q0 plus A Q0 plus, I call this, let's call them A0, B0, sorry, I missed the indices 0 here, everywhere. A0, B0, A0, A0 plus B0 minus B0 divided by 1 plus A0, and obviously it becomes equal to Q0 itself. So in this case, we have constructed our function. So this is our function phi of Q, which we precisely wanted to know. So in the linear case, it is very easy. In a non-linear case, we will need to solve an equation for the expected value of our Q bar. But in the non-linear case, it is slightly more complex because there would be not so simple equation for the expected value of any expression depending on Q hat. I will not discuss this in detail. Later on, we may, if we have time, return to this. For example, using Janson inequality, which allows us to estimate the expected value of Q hat, might be useful in that case. But for the moment, let's restrict ourselves to the linear case. So in the linear case, yes. So instead of the original Q hat estimator, if we know that the bias is linear, if it is not linear, we'll make it linear by linearizing. Then we can remove the bias by constructing this function. Okay. So only after the bias has been removed, only in that case, we can consider our problem to be solved. Without that, as our example with the Ornstein-Uhlenbeck process tells us, we may get very, very seriously deeply wrong. Okay? So that's probably the most important message I would like you to remember, is that we need to check the output of our maximum likelihood or whatever any other calibration or parameter estimation method, check it for being at least unbiased. You may ask me, but how? How do we know this formula for the bias? What can we do to that end? And this is not at all easy. But we'll make a short break now, and then we'll develop a constructive hands-on procedure which will allow us to solve the problem for the bias and construct our original unbiased estimations. Okay, 5 to 10 minutes break now, and we'll continue. Okay, ladies and gentlemen, we are continuing. Okay, are you alive? Not too difficult? Everyone is fine?
Yes, sure.
Great, okay. The lecture is fun. You know what? I was thinking about we'll do it next time. Even a more interesting topic, which is, I may still, because I will do it for another course tomorrow. It will be mathematical modeling of the COVID outbreak using ordinary differential equations with delayed arguments.
Can you please repeat the last idea?
Mathematical modeling, it's not what we are going to do now, it's what we are going to do tomorrow. But I will record it and you will be able to see it as well. Mathematical modeling of the current COVID-19 outbreak using ordinary differential equations with delayed arguments. So a mathematical method which allows us to model physical, economical, or other phenomena where the cause and effect are separated from each other by some time distance, which in particular is suitable for mathematical modeling of epidemic outbreaks like what unfortunately we're experiencing now. So tomorrow we'll be talking about to the fourth year bachelor students, we'll be talking about this kind of modeling. And I will record this lecture for you and you will be able to see it as well. Okay?
Can you please upload the video of the last lecture?
Oh, yes, definitely. So they're all on my local computer. Today I will put them on YouTube in the hope that you can see them more easily using
Okay, and the slides too, if you can.
with slides. Okay.
This notebook, I mean.
Okay. So let's put them on YouTube first, and then where necessary. Not responding. Using slides as well. 1 second. Are we alive? I don't think so. Oh yes, we're okay. So in this very simple situation, if we know our coefficients A0 and B0, and we know that the bias model is linear, so that the bias, then everything is easy, as you understand. And, oh, just a second, what the president says? The president said that the off period is extended until the end of the May holidays. We are still continuing to be on self-isolation. Okay, as expected. So that's the bias. Okay. In this case, it is simple. The bias is a linear function. But the question is how to find it in general? How to construct the bias? How do we know the structure of the bias? And to that end, we may be able to obtain it analytically. So how to find this function bias of the true value Q0? The answer is analytically in very restricted cases, and it is tedious. So it really requires us to work very, very closely with the properties of the corresponding distributions. Typically, it is very difficult. I would say extremely difficult. But you know what? We here are not really mathematicians. We are applied mathematicians. And applied mathematicians are different from pure mathematicians by the fact that if something is extremely difficult, and extremely difficult means impossible or infeasible or will take 100 years to derive, then we can always devise a better method of doing that. So if we can't do it analytically, then any idea, what should we do? What do you think? If there is no analytical solution, we can't obtain it for the bias. What should we do?
Some approximation.
Numerical approximations, you are absolutely right. And the procedure for numerical approximations is actually an easy one. I propose the following algorithm, which is very, very easy to implement. So at the top level, we will generate different values of Q0. Okay? So the outer loop generate somehow randomly, deterministically, somehow generate the values of Q0. Internally, for a given Q0, generate I would say M passes of our stochastic process of the process ST. So there would be, each pass would be S0 and so on Sn, and there are M of them from 1 to M. Okay? Whether they should start from same S0 or not, we can try both ways. Same initial generate randomly, of course. I presume you are familiar with Monte Carlo methods and Monte Carlo generations, right? If not, we'll explain this in detail sufficient to implement this. Have you ever been implementing any Monte Carlo based, let's say, random simulations or random using random number generations in your software? No? Okay. If not, we'll describe how to do it. For the moment, let's say we can, using the pseudo-random generator of your favorite programming language, we can generate a family of passes, M passes, each of length n. Each pass of length n. Okay. Number 3, nested. I deliberately do them nested. For each pass, run the MLE estimator, run the MLE, and obtain Q hat M estimated params, estimated parameters. Okay. Once for each path we obtained the estimated parameters, we can construct the expected value. Okay. Why is it so slow? Wait. No, don't crash. Wait. Scrolling becomes a problem. A second, I may need to close some other applications to free up the memory. Are we any better? Possibly. Okay. Number 4. Compute the expected value of our QM, expected value of Q hat, being just the average 1 divided by M, sum from M being 1 to M, QM. Okay? So basically, starting from a given Q0, construct a number of random passes. For each path, estimate back the parameters. We got an estimate, computed the expected value. Number 5. Now we have the bias. Compute bias of this Q0, because we know the Q0 we started with, right? Which is precisely the estimated value of Q minus the Q0 we started with. And now when this bias is evaluated for a large number of initial points Q0, number 6, I would say approximate bias of Q0 by a linear function. How? For example, using the least squares method. Okay, so that's the algorithm which allows us in general for any distribution to first of all construct the maximum likelihood estimator as described above, but also eliminate the bias from this estimator. And that's a nice thing, isn't it?
Sorry, can I have a question?
Yes.
So we are generating a lot of I don't know, for example, stock prices, and with the sum Q, right? And this Q
with the
is
same Q0 here, yes.
This Q0 is the same for every generated data, right?
You see, there are multiple loops here. So the outer loop, so this is loop for Q0, for multiple Q0s. But now inside here, for a given Q0, inside the Q0 is fixed. We generate multiple passes back estimate our parameters qm, whereas q0 we do know, compute the expected value, and for that given q0, we compute the bias at that point q0. And now outside this loop, when we computed the bias for one value of q0, another, yet another, then we got a collection of biases at different q0 points. And once we got this collection of biases at different q0 points, then we approximate this collection by a linear function, for example, using the least squares method. Something
Okay,
like
thank you.
Okay? It doesn't need to be a linear function. So here, alternatively, it might be that other functions would need to be applied. Other nonlinear bias functions can be used. But the problem is, if you remember, if the bias is a linear function, then we know very easily how to correct the original result using this linear bias function. If the bias is non-linear, then it becomes much more, not much more difficult, but more difficult, and you would need to solve it on a case-by-case basis. For that reason, if at all possible, I would recommend initially model the bias as a linear function. So that's the way. Now how we can use it, actually. So, okay, we have estimated the parameters. In quantitative finance, how can we use this parameter estimation? What it is all for? We actually took a great deal of effort deriving, first of all, the maximum likelihood estimator, possibly using Fokker-Planck for the density, or locally normal approximation, with F transform, then somehow solved this, obtained first the biased approximation, then developed the bias correction method. That's, by the way, something very, very, I would say, a kind of core skill or methodology which each and every financial quant must really be able to carry out. So you may, in your real life as a quantitative analyst, experience precisely this type of problems for statistically estimating the parameters, and you don't know whether your estimation is biased or unbiased, then you really need to run this numerical approximation algorithm, and you arrive at some reasonable solution, which eventually allows you to make decisions about the stochastic behavior of your assets. So, okay, suppose that we now obtained the unbiased estimation. Scrolling once again. Oh. Okay. So, what can we use it for? typically, this type, okay, we're back alive. Okay, so finally, well, we still didn't obtain Q0 exactly, but we have obtained Q bar, which is unbiased estimation of the true Q0. So the expected value of Q bar is now equal to Q0 exactly. In the same process, by the way, in the algorithm described above, we can also estimate the standard deviation. The standard deviation of this expected value, the standard deviation of Q bar minus Q bar minus Q0 Q bar minus Q0 is also can also be estimated, and ideally it should be proportional to something like 1 divided by the square root of n, where n is the path length. You remember. If the standard deviation is, for example, is constant or is not decaying with n, so it would be, for example, of 1, this is an unfortunate situation, which means that although the expected value of our estimated parameters is really equal to the true parameters, but it doesn't help us to take the longer and longer and longer path. We still have exactly same type of standard deviation between the true and the estimated values of parameters. So if this happens, this is not a very good idea, but that's the property of the model. For example, if in a very simple, let's say a very simple linear model with just a linear trend and a Brownian motion, the trend itself cannot be estimated with this asymptotic accuracy. For example, inversely standard deviation inversely proportional to the square root of n. It doesn't really help you how many points you select along the path. The standard deviation would be really of this constant order of magnitude. By the way, that's a good example. Let's describe it in a little bit more detail. So suppose that there is a simplest model, simplest of all possible kinds. DST, forget even about, this is a Brownian motion with drift. Forget even about the geometric Brownian motion. It's just a Brownian motion with drift. DST equals to a constant mu. I will denote it by mu0 in accordance with our Q0 true values. Mu0 times dt plus sigma 0 dwt. So this is a Brownian motion. This is some kind of non-zero drift. And suppose that again we have a time series from t0 to tn equals to t capital, and for each from 0 to t capital, and for each instant of time we have s0 and so on, Sn value of our process. Okay, so the question is, how would we estimate our parameters, let's say mu0 and sigma 0? What we can say, we can, let's do it just formally, why not? We will apply, I think we have already done something like that for the geometric Brownian motion setup. We can now do it we can now do it in a more simple even case for this linear Brownian motion with drift. So basically this means that according to this model, Si minus Si minus 1 would be equal to mu0 to I, where to I is again Ti minus Ti minus 1, plus sigma 0 delta W, let's say I, where this delta Wi has a normal distribution with 0 mean and the standard deviation being equal to the square root of 2I. Okay, which means that with 2I being fixed, well, known at least, this all these random variables Si minus 1, they have, I wouldn't say exactly same distribution, but so let me denote this possibly by delta Si, but they would have distributions only different by the trend value and this delta and the standard deviation of delta Wi. Therefore, the expected value, I am not using the maximum likelihood here. I am using a different method, which is simpler in this case, but we can use both actually. This is a method, effectively method of models, of moments. Method of moments. There are several ways of how we can estimate our parameters. Let's do method of moments for the moment, and then we'll possibly use the maximum likelihood as well to arrive at exactly same results. So with the method of moments, we have the expected value of each delta Si would be equal to, the expected value of this part is 0, would be equal to mu0 times 2I. And therefore, the expected value of delta Si divided by 2I, we do not assume that all intervals are same. If they are same, then it becomes even more simple. But the expected value of delta Si divided by 2I is mu0. And therefore, this mu0 can be estimated as 1 divided by n. How do I estimate the expected value of delta Si divided by 2I? It can be estimated as 1 divided by n, sum from I1 to n, precisely delta Si divided by 2I. And therefore, it is not the exact mu0, but mu hat would be equal to the estimated quantity is precisely 1 divided by n, sum from I1 to n, delta Si, and you understand that delta Si is Si minus 1, divided by the corresponding interval to I. For sigma, we will estimate the sigma in the next step. For the moment, let's see what we got here with mu hat. Mu hat is a random quantity, is a random variable, because delta Si can be considered as a random. Scroll. If it continues like that, I will have to reboot. But we are more or less okay. Scroll. Okay. Scrolling. No. Okay. Here we are. Wildlife. Now, what can we say about the expected value? First of all, is this estimation unbiased? We don't know, but let's check. The expected value of mu hat as a linear function is 1 divided by n, sum from I equals to 1 to n, because it is a linear thing, 1 divided by 2i, because 2i suffixed, the expected value of delta Si. But delta Si, as you remember, it is Si minus 1. It is mu 0 times 2i plus sigma 0 delta Wi. And therefore the expected value of delta Si is equal to mu 0 to I. And therefore we immediately get that the expected value of our estimation mu hat is indeed mu 0. Happy are we? Mu hat is unbiased, right? Great. But now let's see what is about the standard deviation or quadratic variance of mu hat. Let's say quadratic variance of mu hat is the expected value of mu hat minus its expected value, which we know mu 0 squared. Okay, let's see, equals to the expected value of, and now we have to expand it. It is a really expected value of 1 divided by n, sum of I1 to n delta Si divided by 2i minus mu 0 squared. Which is actually, by expanding this, we can rewrite it, because there will be expected value of let's see what would be the easiest way. Oh, okay, that's okay to do it like that. So it is 1 divided, we have n squared here due to squaring the whole sum. So it is 1 divided by n squared. Let's do this one. 1 divided by n squared, expected value of, and now the square of the whole sum from I1 to n. I would say delta Si minus mu 0 to I divided by to I and all sum is squared. Okay. What is delta Si minus mu 0 to I? It is precisely this. It is sigma 0 dwi. Therefore, it is 1 divided by n squared, expected value of sum from I1 to n, sigma 0 dwi divided by 2I squared. Okay. Now it is very important. Let's continue. So it is 1 divided by n squared. Now we really need to square up the arguments. Okay. Moreover, you see that there is a sigma 0 everywhere. Therefore, sigma 0 squared can be factored out of the sum and of the expected value. So we have sigma 0 squared, sigma 0 squared divided by n squared. Expected value of the sum from I1 to n delta wi divided by 2I squared. Continuing, sigma 0 squared divided by n squared. And now we open up the sum, expanded. We expand the sum. Expected value of, first of all, sum from I1 to n delta wi squared divided by 2I squared plus cross terms 2 times sum from I1 to n sum from j, let's say they must not overlap. So if I is from 1 to n, then j starts from I plus 1 to n. For this reason, actually, I wouldn't end with n. It would end with n minus 1, but it doesn't really matter here. The cross term, delta wi delta wj divided by 2I to j. Now, a challenge once again, scrolling. Wait. Okay, running. Okay. Now it is equal to sigma 0 squared divided by n squared, sum from I1 to n 1 divided by 2i squared expected value of delta wi squared plus 2 times sum for I, sum for j, 1 divided by 2i to j, expected value of delta wi, delta wj. What can I say about this? We can say that the expected value of delta wi squared, remember that delta wi has a normal distribution with 0 mean and the standard deviation being the square root of 2i. Remember? Therefore, the expected value of precisely delta wi squared is the square of the standard deviation, is 2i. Okay? Whereas here, by the property of the Brownian motion, we deliberately constructed the sum you see here from I1 to n minus 1 and j from the next one from I plus 1 to n. These delta wi, delta wj are not equal and never overlapping, because we always have here j being greater than I. Therefore, the expected value of two non-overlapping, non-equal increments of the Brownian motion, because of their independence, is 0. And that's a very important thing to remember. Therefore, the whole cross term vanishes, and we eventually have sigma 0 squared over n squared. And here we have sum from I1 to n, 1 divided by 2i, because this expected value is equal to 2i, and we have 2i squared in the denominator. Okay, so we got this. By itself, it does not tell us much, but now let's say simplify, simple case. All 2i are constants. And if they are constant, then each interval is equal to the general length of our period divided by n. Because you remember we had Tn being equal to T capital, T0 being equal to 0. For this reason. Then continuing in this simple case, we would have sigma 0 squared over n squared, sum from I1 to n, 1 divided by 2i is n divided by t. And n divided by t is a constant. Therefore, we factor it out from the sum. Therefore, we have sigma squared 0 over n squared divided by, n divided by t, and times n, because the sum would still contain n units. And therefore, n squared cancels, and we have sigma squared divided by t. That the variance of our, what we're we're computing that the variance of our mu hat. Therefore, the standard deviation of mu hat, of our estimation of mu hat, equals to sigma 0 divided by the square root of t. Discussion. Let's turn on the microphones and discuss what we got. We got something extremely remarkable and extremely unpleasant. What have we got? What can we say about this result? Your ideas, please. Look at this final formula. Anything odd you
I
can
think
notice?
it's strange because capital T can be whatever value, so I think it doesn't make sense.
Well, capital T is the length of our observation period. It has a perfect physical or financial or mechanical sense. We have observed our stochastic process over the interval of length t. So, for example, if t is measured as is normal in finance, is measured in years, let's say t is, let's say, 1/4 of a year. Then we have observed it within just 3 months. That's normal. But you see, the problem is the standard deviation of our obtained estimation mu hat doesn't depend on n. Eventually, after all our transformations and simplifications, n disappeared from our final expression. So, what does it mean that this standard deviation, you remember this desirable property, that this standard deviation depends somehow inversely on n, maybe it is proportional to the square root of n inverted, and in this case, when n tends to infinity, the standard deviation would tend to 0. But in this case, it is not true. So, the more points we have this observation period, okay? We have this observation period from t0 equal to 0 to tn equals to t capital. In between, we have some points ti where we make our observations of our random variable. So, for example, we observe the price, if st is a price. And one would expect that the more points we have, so for example, the more frequent grid of points we get, the more accurate our estimation of, let's say, mu would be. But it is not. It absolutely doesn't matter. So, for example, if t is 1 year, it absolutely doesn't matter whether we took just 2 points within a year, let's say 1 point at the beginning at t0 and 1 point at the end of the year, or we took our observation of the random variable every day or even every minute within this year, the standard deviation of our estimated mu, of our estimated trend, is still the same. It is sigma 0 divided by the square root of t. So taking more and more and more frequent points doesn't help at all, doesn't help us at all to produce a more accurate estimation of mu. Can you imagine this? Doesn't help. Taking longer intervals, yes, it does. But more frequent sampling does not. And that's very unfortunate, because this means that in order to estimate the trend mu, with sufficient accuracy. We would like, obviously, this standard deviation of mu being as close to 0 as possible. It is not enough to have frequent sampling. It doesn't depend on n. We really need to wait for a very long time. Maybe just making two measurements, two observations, one at the beginning and another one at the end. But still just wait long enough, wait and wait and wait and wait in order to estimate our mu more and more accurately. Frequent sampling doesn't help. On the other hand, for sigma, the situation would be different. I'm probably not going to derive, it may lead to a little bit tedious computations in this case, but I can tell you that basically the standard deviation of sigma estimation would tend to 0, I think inversely proportional to the square root of n, as n tends to infinity. And in that case, it would indeed be advantageous. Actually, we may try to do it, why not? So let's estimate sigma, but we would, in order to reduce writing, make this simplifying assumption that all our intervals are equidistant, of equal length. Scroll. We're done. Okay. It was lagging and lagging and lagging and crashed eventually. Can we recover it? Doesn't allow us to recover. Okay, never mind. So once again, now we would like to estimate the sigma. Once again, Si minus Si minus 1 equals to mu times, and for the mu we already got an estimation, mu times tau I, and we would say all tau i's are in this case equal to T over n for simplicity, mu 0 plus sigma 0 plus sigma 0 delta W I. Okay. Therefore, Si minus Si minus 1 minus mu 0 to I, assuming that mu 0 is known. In fact, it is not, and we need to substitute an estimate instead of it. But for simplicity, just to show you the asymptotics, we will assume that mu 0 is known. It doesn't change anything significantly. Would be equal to sigma 0 dwi. And therefore, we would say that sum from I 1 to, yes, and this right-hand side would have the normal distribution with 0 mean and the standard deviation being equal to sigma 0. So this would be denoted by a constant tau, sigma 0 square root of tau, just for simplicity. Okay, and in this case, if we know that it has 0 mean, then we would say sum from I1 to n. The left hand side squared si minus 1 minus mu 0 to squared would be equal to sigma 0 squared sum from I1 to n delta wi squared. Now applying the expected value operator to both sides, we would have this. The expected value of delta wi squared is obviously equal to tau. Therefore, it is equal to sigma 0 squared tau sum from I1 to n, just 1. Therefore, it is n. Therefore, it is sigma 0 squared n tau. And n tau is precisely our duration t. So this is equal to sigma 0 squared t, whereas the left-hand side and the expected value can be estimated as the mean. And therefore, we can say sigma 0 squared t can be estimated as what is the as the expected value of this, and the expected value is just 1. Sorry, it's okay. It had zero mean, and therefore the expected value of this sum is just sum of you can say this then we estimate it as sum from I I1 to n s I minus s I minus 1 minus mu 0 to squared. Just a second, whether we, and therefore we would have sigma squared is 1 divided by t, sum from I1 to n, si minus s I minus 1 minus mu 0 to squared. In this case, no, actually, it's going to be a little bit too tedious. I think we simply not have enough time. We may start from this point later on, but I don't think it is a good idea to do it now, because what we need to do is, first of all, to prove that the expected value of the right-hand side is really equal to the left-hand side. So this estimate is unbiased. In fact, it is. The estimation for sigma sigma hat squared is unbiased. But at the same time, we would need to construct the quadratic variance of it, and probably okay, but we don't have enough time actually for that now. I will we may actually do it next time, or we may I may send you this as a separate addendum. So it is possible to show that the variance of sigma hat squared indeed tends to 0 as n tends to plus infinity in this case. So sigma is both actually unbiased, just requires a little bit more effort to do it, and has asymptotically, so basically it is unbiased and efficient, actually efficient, because it's the variance of the estimation itself tends to 0 as n tends to plus infinity. This says that actually the volatility of our stochastic process is more easy to estimate than the trend. So for the trend, we really need to wait for a long period of time in order to get its standard deviation decay sufficiently. For the volatility, it is sufficient to have any, let's say, maybe not so long interval of time, but over that interval of time, we would have sufficiently many points n, points at which this observation was made, and in that case, by taking more and more frequent observations within the same time interval, we would still be able to produce sufficiently accurate estimation of sigma squared, which is what we probably want to see. Physically, why do you think this happens? So you see, sigma is easier to estimate. Let's just conclude our discussion for today by a physical argument. Why do you think sigma is easier to estimate than mu? For mu, we have to wait for a long time. For sigma, we just need to take frequent observations over a limited t, and we're okay. Why is that? The answer is because sigma is really more pronounced than tau. Look at this equation once again. You remember that delta Wi as an increment of the Brownian motion, yes, we know, it has a normal distribution with zero mean and the standard deviation being square root of tau. Therefore, this delta Wi is of order of magnitude being the square root of tau. Whereas, whereas the coefficient at mu is proportional to tau itself. Once again, for a small tau, the effect of the Brownian motion here is the infinitesimal quantity with respect to tau of lower order. Lower order means more pronounced effect than the effect of tau. So if this is tau, this is a linear function here at mu0, but this is a square root, so this is tau, this is a square root of tau. Obviously they intersect at 1. So for small taus, the square root is by far more pronounced. Remember that tau is in years, we are talking about very small time interval, so that's 1 year. We're much below 1 year. So the effect of taking the square root of tau mean that sigma 0 is multiplied in general by much larger quantities than mu 0. So locally, sigma 0 is by far more, let's say, important and pronounced. Let's say the effects of the trend are swamped by the effects of the volatility. And that is the thing to remember. In short term, the effects of the volatility in any price process of our financial instruments are by far more pronounced and more important than the effects of the trend. That's why the trend is actually much more difficult to determine. We applied the method of moments. You remember, you see, we computed the first moment, which is the expected value, and the second moment, which is the quadratic variance. And then from them, we estimated the mu and sigma. Exactly same results would be obtained if we applied the maximum likelihood estimation. In this case, for a normally distributed process, the results would be the same. So same results from MLE. This is another interesting property of a process which is a Brownian motion, which means that you see the Brownian motion accumulates its quadratic variance. What is quadratic variance? It is a square of the increment of the process minus its expected value. It accumulates over the path from I1 to n its quadratic variance linearly over time. In the left-hand side, we have this sigma 0 squared times t. In the right-hand side, we have the quadratic variance accumulated by the process along its path. That's probably all for today. Next time, we will continue with two-dimensional processes, which I touched upon today, but then it appeared to be a little bit too premature because we didn't finish with the one-dimensional ones. Please ask the questions.
Can I ask a question?
Yes.
Please don't forget to upload the previous lecture, like to follow.
I will try to do it tonight. Yes. Yes. Thank you
Yeah.
for your reminder. I will try to do it tonight. These are huge files. After I finish my lecture, my computer takes about half an hour to compress our Zoom session.
Okay. And
I will try to upload. Let's see how Google YouTube would cope with this load.
Okay, and can you please provide some reading materials about the same?
Oh, yes, of course. If I did not, I will definitely post it right now. And by far the most, I think, useful book is Stephen Schritt's Stochastic Calculus for Finance, Volume 2. I don't like Volume 1. It is about discrete time models. We have been working, as you can see, in continuous time models all the time. So our main instrument are models based on the Brownian motion. That's about this second volume. I will upload them into our Telegram group, not just references, but books themselves, so you can download them.
Okay, and I mean, if you can specify like more specifically about the case when we have a vector of like here we're discussing one-dimensional or two, or if we have an n-dimensional vector of stochastic variables and how to do this kind of estimation, because it's
yes.
you can
Let me put it that way.
To read or
all right, you are right. So the big quantum leap is in between dimensionality 1 and dimensionality 2. Once we learn how to do it in 2 dimensions, then it is absolutely trivial to extend it into more dimensions. So next lecture will be about the 2 and n-dimensional cases.
Okay, thank you.
Thank you. Any other questions?
Thank you. Goodbye.
Wonderful. Okay, thank you. Thanks.
Thank you.
Thanks a lot to everyone once again.